Welcome to the deep dive. We're here to, well, cut through the noise and focus on the knowledge that really matters. And today, we're diving deep into something absolutely fundamental, network fundamentals. I mean, seriously, everything we do online, emails, calls, streaming, it all happens over networks. Understanding this stuff isn't just for the IT crowd anymore. It's, essential for everyone. For this deep dive, we've pulled key ideas from some great material, specifically a foundational training video for the Cisco Certified Network Associate, the CCNA. It really focuses on the absolute basics, laying that groundwork.
Right, and that's really our mission today. We want to pull out the most critical, the core concepts of computer networking.
Yeah.
These are the ideas that form the base for understanding almost, well, any digital interaction you have, stuff that'll be relevant for years. This isn't just about getting certified. It's about really grasping how our connected world actually works underneath it all.
Okay. Let's start right at square one. What is a network exactly? Because, people hear network and they often think Facebook, right? Social networks. But we're talking about something different, the actual plumbing, the connections.
Exactly. The source we looked at had this great analogy, the king's messenger. Think way back. A king needs to send a message. He gives it to a messenger. The messenger uses a road, goes through maybe some gates to reach another king. In that picture, the message, that's your data.
Yeah.
Your documents, your pictures, videos, whatever. And the road, that's the network itself. The whole point, just like that messenger, is communication. Getting information from one computer to another. Simple as that, really.
But here's the kind of magic part, isn't it? You've got Windows machines, Macs, Linux boxes, phones, servers, all totally different systems, yet they talk to each other perfectly. How does that happen? How do they, understand each other?
Yeah, it seems complicated, but the reason it works is global standards. The source mentions things like the OSI models. Think of the OSI model as like a shared rule book, a recipe maybe. It defines exactly how computers should package and send information. So every device, no matter who built it, is essentially speaking the same networking language. That shared set of rules is what makes it all possible.
Okay, got it. Standards are key. So let's drill down. What's the absolute simplest network you can have? Like two computers.
The very simplest is just connecting two computers directly with a wire. That's typically an Ethernet connection. You'll use an Ethernet cable. You've seen them, probably blue or yellow. Inside, it's got 8 little copper wires. These end in that plastic clip, the RJ45 connector.
The thing you plug in.
Right, and that plugs into a port on your computer, which is part of the network interface card, or NIC. The NIC is like the computer's doorway to the network. So that basic two-computer link, that's Ethernet.
Okay, simple enough for two. But what if you've got, 10 computers in an office? You can't just run cables between every single pair, can you?
No, definitely not. That would be a total mess, incredibly complex. So for more than 2, you introduce a central device.
Yeah.
Usually that's a network switch. You might hear the term hub sometimes, but switches are much smarter.
Smarter how?
Well, a hub just repeats any data it receives out to all the connected computers. It's like shouting in a crowded room. A switch is more like a targeted delivery. It knows which computer the data is for and sends it only to that specific computer. Much more efficient.
And how do the computers know which computer is which on this network with the switch?
That's where IP addresses come in. Each computer gets a unique address, like a house number, so the switch knows exactly where to send the data packets.
Okay, so switches and IP addresses let many computers talk efficiently. Let's tie this back. What's the big why for businesses here? What problem did networking solve that was maybe less obvious than just communication?
Oh, it's fundamentally about efficiency and, frankly, cost savings. Huge cost savings. Think about an expensive piece of equipment, like a really good laser printer or a high-speed scanner. Before networks, if 10 people needed to print, you might have had to buy 10 separate printers, even if they only printed occasionally.
Wow, yeah, that sounds incredibly wasteful.
Exactly. With a network, you buy one good printer connected to the network switch, and all 10 people can share it. It allows companies to share expensive resources instead of duplicating them everywhere. That frees up a significant amount of IT budget. It completely changed resource management.
Okay, so we've got our office network, sharing printers, everyone's happy. But what happens when that office needs to connect to another office across the country? How do we scale up from this local setup?
Right, so that local setup, the office network, your home network, that's called a LAN, a local area network. It's confined geographically. Now, connecting LANs over long distances, that's where WANs, wide area networks, come in. Imagine your company has an office in New York and another in, say, Boston. You could try to lay your own private cable between them.
But that sounds incredibly expensive and difficult.
Prohibitively so for most. So instead, you rely on internet service providers, ISPs. ISPs have already built these massive high-speed networks. They're backbones that span cities, countries, continents. So your New York LAN connects to your ISP there. Your Boston LAN connects to the ISP there. The data travels across the ISP's backbone between the cities. The ISPs provide the infrastructure for these WAN connections, linking your separate LANs together over huge distances.
So the ISP handles the long haul bit. And how does the internet itself fit into all this? Is it just a really, really big WAN?
That's a pretty good way to think about it, yeah.
Sure.
The source describes the internet as a very massive WAN which covers the entire world. It's essentially a massive network made up of countless interconnected WANs. Think of all these different ISP backbones, university networks, company WANs, all linked together globally. That's the internet.
Okay, that makes sense. So when we use everyday apps, YouTube, news sites like CNN, shopping on eBay, making calls on Skype, how are they using this giant interconnected network? What's happening under the hood, basically?
Well, in a simplified way, services like YouTube have powerful computers called servers. These servers store all the videos and web pages. Google, for instance, places these YouTube servers onto the internet, making them publicly accessible. So when you type youtube.com in your browser, your computer sends out a message. It's called an HTTP request across the internet to find the right YouTube server. It's basically asking, hey, can I see the YouTube homepage? The server gets that request, finds the requested page or video, and sends the data back to your computer. Your browser then takes that data, usually an HTML file, plus images, video streams, etc., and displays it for you. That request and response cycle is fundamental to how most of the web works.
Got it. Request, response, across this global web of networks. Now let's talk speed, network speed. It feels simple, but there's a common trap, right? The whole bit versus byte thing.
Oh, absolutely. This trips up so many people. It's crucial to get this distinction right. A bit small b is the smallest piece of data, a 0 or a 1. A byte, capital B, is a group of 8 bits. Now here's the key. When we talk about how big something is, like a file size or computer memory, we always use bytes, megabytes, MB, gigabytes.
Yeah, like my phone has 128 gigabytes of storage.
Exactly. But when we talk about network speed, how fast data travels, we always use bits per second. Megabits per second, MBPs, gigabits per second, GBPs.
Ah, okay. So speed is bits, size is bytes.
Correct. And because there are 8 bits in a byte, a 1 megabyte per second MBP speed is actually 8 times faster than a 1 megabit per second MBP speed. Big difference.
Wow. Okay, that's a huge difference.
It is. And just one small extra detail in computing, kilo usually means 1024, not 1,000. So 1 kilobit is 124 bits. 1 kilobyte is 1024 bytes. It's a binary thing.
Okay, let's make that concrete. You gave an example in the source transferring a 128 kilobyte file over a 1 megabit per second connection. How does the math work there to show how long it takes?
Yeah, it's a perfect illustration. So you have a 128 kilobyte KB file, that's size, so it's in bytes. Your speed is 1 megabit per second, MBP, so that's speed, so it's in bits. First, convert the file size to bits. Since 1 byte, 8 bits, you multiply 128 kilobytes by 8. 128.8 equals 224 kilobits.
Okay, 124 kilobits.
And 124 kilobits is exactly 1 megabit. And
So the file size in bits is 1 megabit.
Precisely. And since your connection speed is 1 megabit per second, transferring a 1 megabit file takes exactly 1 second.
That really clarifies it. The units have to match. Bits for speed, bytes for size, and remember the factor of 8. But, speed isn't the whole story for network performance, is it? The source mentioned 3 critical factors: speed, delay, and availability.
That's right. They all work together. First, speed. We just talked about bits per second. But the important thing here is that your overall speed is limited by the slowest link in the entire chain. Imagine sending that file from Bangalore to New York again. It might cross a slow link here, a fast link there, another medium link.
Like hitting traffic on the highway.
Exactly like that. Even if you have a super fast connection leaving Bangalore and another one arriving in New York, if there's a slow 1 Mbps link somewhere in the middle, the whole transfer can only go as fast as that 1 Mbps bottleneck allows.
Okay, bottleneck effect. What about delay?
Delay is about how long it takes for the first bit of data to get from the source to the destination. It's affected by 2 main things: distance and the number of hops or devices the data has to pass through. Every router or switch the data goes through adds a tiny bit of delay. So sending data from New York to nearby Boston will naturally have less delay than sending it all the way to Bangalore, just because of the shorter distance and likely fewer hops.
Right. And that's related to those CDNs you mentioned earlier, content delivery networks.
Precisely. CDNs work by reducing delay. Instead of everyone fetching a YouTube video from a server in California, Google puts copies of popular videos on CDN servers all around the world. So if you're in Singapore, you connect to a nearby server in Singapore. Much shorter distance, fewer hops, much less delay. Makes streaming way smoother.
Clever. Okay, so speed, slowest link, delay, distance, and hops. What's the third one? Availability.
Availability. This one's pretty straightforward. For the communication to work at all, every single link in the path between the sender and receiver has to be up and running. If any one of those connections goes down, maybe a cable gets cut or a router fails, the data might not get through. Or if the network is smart enough, it might try to find an alternative route, but that detour could be much longer, increasing delay and potentially reducing speed. So availability is just fundamental reliability.
Speed, delay, availability. Got it. Okay, one last core concept to unpack. Network topology. What does that mean?
Topology is basically the layout or the map of the network.
Hmm.
How are all the devices physically or logically arranged and connected? There are a few fundamental types, even though real networks are usually combinations.
What are the main ones?
Yeah. Well, there's the star topology. Imagine a central point, like a switch, and all the computers connect directly to that central point, like spokes on a wheel.
Okay, like our office example earlier.
Exactly. The big benefit is if one computer's cable fails, it only affects that one computer. The rest of the network keeps working. Then there's the ring topology. Here, computers are connected to each other in a closed loop like a circle. Data travels around the ring. An advantage here is some redundancy. If one link breaks, data can potentially travel the other way around the ring to reach its destination.
Makes sense. And the last one?
The bus topology. This is simpler. All devices connect to a single shared cable, the bus, like houses along a single street. Data travels along the bus, and devices listen for data addressed to them. The downside is, if that main cable breaks, it splits the network. Devices on one side of the break can't talk to devices on the other side.
Star, ring, bus. So if those are the basics, what do modern networks actually use? Are they just one of these?
Not usually, no. Real-world networks almost always use a hybrid topology. They mix and match. Think back to the office. The PC's connecting to the switch. That's a star. Simple, easy to manage individual connections. But then how do you connect multiple switches together? Maybe across different floors or buildings. You might connect those switches using a ring or maybe even a bus topology between them. This provides redundancy. If one link between switches fails, traffic can often reroute through another path. So you get the best of both worlds, the simplicity of the star for end devices and the resilience of ring or bus for the core connections.
Wow, okay. We've really covered a lot of ground. From just two computers and a cable, all the way up to how the global internet works, how data travels, the importance of speed, delay, availability, and even how networks are structured with topologies. It really does underscore how vital these fundamentals are. They're literally underpinning everything we do digitally.
Absolutely. I mean, it makes you think, doesn't it? Our whole digital world is built on this complex web. Data flow is limited by the slowest link, affected by distance, needs every piece to be available. So as we demand faster, more instant, more reliable connections globally, what comes next? What are the new challenges or possibilities building on these timeless principles? What's the next evolution going to look like? Something to ponder.